Hello students, in physics in the section heat we are going to see another experiment now. The experiment is about verifying Newton's law of cooling. Do you remember studying Newton's law of cooling? What does it say? It says the rate at which an object cools is proportional to the difference in temperature between the object and the object's surroundings. Let's say you have a surface, right, which is at theta 1 and the surrounding is at theta 2, and let's say theta 1 is greater than theta 2. So what will happen? The heat will be transferred from theta 1 to theta 2. From this object to the surrounding, heat will be lost. Heat is being lost means the temperature, the theta 1 will start falling. Temperature will start falling, which is what we call cooling rate. The rate at which temperature drops. So the rate at which theta 1 falls, we can call it d theta by dt. In maths they call it d theta by dt. The rate at which t drops with time, basically every second, by how much theta falls. That depends on, or that is proportionate to the temperature difference. This is what Newton's law of cooling states. Right? Repeat again. The rate at which an object cools is proportionate to the difference in temperature between the object and the object's surrounding. We are going to verify this. In this experiment, we are going to see whether this is verifiable, whether we can verify it. How we are going to do it? Look at this. So when you say delta theta by delta t is proportionate to theta minus theta r, then it has to be a straight line. That means if the temperature difference is 0, the cooling rate also must be 0. Why? There is no difference. If this is 0, theta and theta r, that means an object which is at the same temperature of room temperature, an object which is of the same temperature of its surroundings is not going to lose temperature, it's not going to lose heat. Right? Okay. So theta minus theta r, if it is 0, that means theta and theta r are equal, then there is no loss of heat. There is no cooling that happens. Consider this point. Consider another point. When theta minus theta r doubles, let's say theta r, let's say it's 25 degrees. Let's say the object's temperature is 55 degree. Then the difference is 20 degrees, isn't it? 20 degree. When it is 20 degree, at which rate it drops, at which rate it cools down. And then let's say when it comes down to 45 degree, then the extra temperature is 10 degree. At that point, at what rate it cools down, at what rate its temperature falls, d theta by dt, it will be double, it will be half. That means here if it is, let's say, the rate is R1, here it is R2. Since this has doubled, R1, R2 also must be double. Understand? So basically when they say it's proportionate, okay, let me speak a little bit of maths here. If you take delta Q by delta T, if you make it equal, you have to put a constant on the other side, theta minus theta r. Now look at this. This is what we have taken in the x-axis. This is what we have in the y-axis. I told you this is a constant because the proportionate sign, when you want to make it equal, you give a constant. Y equals mx. You know y equals mx plus c is a straight line. Here there is no c, that means there is no intercept, which means it must be a straight line going through origin. Origin. What is this delta Q by delta T? Going back to this object, the heat content of this will be mc theta. M is its mass, C is the specific heat capacity, theta is the temperature. So with time, when it loses heat to the environment, Basically, the Q, the heat content reduces. But M and C are constant. M and C are constant. So I can say delta Q by delta T, if you take delta MC theta over delta T. But M and C are constant, that doesn't change. You can take M and C out, delta theta by delta T. So actually the term cooling rate, that refers to delta theta by delta T, the temperature falling rate. But temperature falling rate and the heat content falling rate are going to be proportionate. Why? MC is a constant. So I can say delta Q by delta T is proportionate to delta T by delta T. So what the law says is delta theta by delta T is proportionate to theta 1 minus or theta minus theta R, the excess temperature with the compared to the surroundings. Whereas this is proportionate to delta Q by delta T, therefore I can say delta Q by delta T is also theta minus theta R. Clear? Right. So cooling rate or the heat loss rate, both are going to be same. Cooling rate means delta theta by delta T. Heat loss rate means delta Q by delta T. With time, how the heat content changes. That's the heat loss rate. Cooling rate means with time, how the temperature falls. Right? Both are going to be proportionate. Both are proportionate to what? The surroundings temperature. Compared to the surroundings temperature, how much excess temperature the object has. Right? That is what we mark it as theta minus theta R. So how we do this experiment? Look at this. We need these apparatus: calorimeter with stirrer and lid, a beaker with water, thermometer, stopwatch, 2 metal containers. Why do we need these 2 metal containers? When I do the experiment, I will explain it to you. This Newton's cooling law can be tested under 2 different conditions. You can use either of the conditions. Condition number 1 says when there is a constant flow of air. That's why in some books they would have mentioned, when you do this experiment, keep this apparatus set up, keep this experimental arrangement near a window and do this experiment. Because then if you are keeping it near a window, we can assume there is almost a constant flow of air. But nowadays getting a fan, electric fan, is very easy, very comfortable everywhere. So instead of keeping it next to a window, you can keep a fan, electric fan, and do this experiment. Why do you keep the electric fan? To maintain constant flow of air. That's one way of doing this. The other setup is to make sure the surrounding does not change. Let's say you are doing this experiment for 15 minutes. For that 15 minutes, the surrounding conditions should not change. Should not change. So it's very difficult to keep the surrounding conditions unchanged. Right? Suppose, let's say when you are doing the experiment, if a person is standing in 20 centimeter distance, entire 15 minutes he has to stand at the same position to ensure surrounding conditions doesn't change, which might be practically difficult. So in physics they found another way, another method to maintain the surrounding conditions unchanged when you do experiments in heat. What that says is, or how we do that is, look at this. You take one container with water and then keep another container with this. Another calorimeter, let's say 2 metal calorimeter. This is one metal calorimeter, let's say C1. This is C2. This gap can be filled with cool water. I'll tell you why we keep cool water. So basically the bigger calorimeter is filled with cool water, and then you submerge another empty calorimeter. You may have to keep some weights here so that the calorimeter is remaining submerged, otherwise it will start floating. Then the environment here, look at this environment. This environment we can assume to be constant environment, constant surrounding. Let's say you keep an object there, let's say a heated object is kept here, it loses heat. What will happen? This is metal calorimeter. So immediately the heat will be absorbed, and this is cool water which has a very high specific heat content, 4200. So water will absorb the heat faster. All the heat released by this substance will be absorbed here. So that this environment within the smaller calorimeter here will remain almost the same. Outside these two calorimeters, if people are standing, walking, it doesn't matter. Any changes happening in this environment doesn't make an impact to the environment here. So this is what we say constant or unchanged surrounding setup when we do heat experiments. So there are two methods to do verification of Newton's cooling law. One is keeping constant surroundings by means of this arrangement. If not, keeping an electric fan and maintaining constant flow of air. Clear? That's why I have mentioned two metal containers can be used to make this arrangement, or if you don't want to do that, an electric fan. Usually electric fan and constant flow of air is considered to be better than any other arrangement. Right? Okay. So those are the apparatus we need. Look at the procedure. See, I have shown you both methods. This is the method where you just keep the calorimeter. Now this is what we are going to do. We are going to heat this water to approximately 80 degree. Right? You measure the room temperature. Let's assume the room temperature to be 30 degree. Let's just assume it. So you hang this here either under constant surrounding setup or with the electric fan and constant airflow setup, this or that, whichever the method, and constantly, right, at equal time gaps, measure the temperature of this. That's why we have this thermometer. Keep stirring it so that the temperature is uniform within the water. Also the surface temperature and the water's temperature are same. To ensure that, keep stirring it. They test this in the exams. Why do you stir it? To ensure or to maintain same temperature on the calorimeter surface as well as within the water. For that purposes, you keep stirring it. So what will happen? First, what you do, you take the temperature reading against time. Initially, the temperature is going to be 80, right? When you are starting the experiment, it's at 80. Then little by little, the temperature has to start falling. The room temperature is 30, means at the end, like if you leave it for a longer time, at the end it has to be 30. Very well, you know that. Let's say you heat the water at home. Let's say you are making a cup of tea and you forgot to drink that tea. You kept it on the table. You come back and see after half an hour. Do you think the tea will remain still at that same temperature? Is it as hot as it was when it was prepared? No. After 30 minutes or after 40 minutes, when you come back after a long time, it might have cooled down and it will be at the same room temperature. So that's what happens. The heat will be dissipated. Heat will be lost to the environment. Right? Temperature falls. From 80, if the initial temperature is 80, it falls down to room temperature. But what we studied earlier in the theory, the cooling rate is proportionate to theta minus theta r. Theta minus theta r means how much excess heat you have compared to the surrounding. So when you are at 80, look at this, when you are at 80, this, let me say delta theta by delta t, if you are not comfortable writing d theta by dt, right, delta theta by delta t or d theta by dt, whatever the rate of change of temperature, initially it's going to be proportionate to, when it is 80, when theta is 80, theta minus theta r will be 50. Then when it comes to 70, after some time, delta theta by delta t has to be proportionate to 40. Why? 70 minus 30. When it is 60, 30. When it is 50, proportionate to 20. If you want to make it equal, you add a constant 50k, 40k, 30k, 20k. So what this means is when it is at 80-degree temperature, the rate at which theta falls is very high. Can you see? It falls at a rate of 50k. K is some constant. I don't have to bother about that. When the temperature comes down to 70 after some time, now this is at T equals 0, after some time, let's say this is the point when theta comes to 70, the drop rate is 40k. Theta still drops, but at a lower rate. When temperature comes to 60, the drop rate is 30k. So when the temperature keeps falling, the rate at which temperature falls also less. We studied about graphs. When we studied mechanics, we studied about graphs. Let me show you some graphs first of all. Right? Look at this. This is a graph where it's a straight line. That means it falls at a constant rate. Falls at a constant rate. Constant rate. It falls at a constant rate. You take 1 second here. You take 1 second here. Wherever you take 1 second, the drop in whatever the y value is constant. A graph like this, look at this. Look at this one. This also goes downwards, but shape is different. It was a straight line, it's a curve. And how the curve is, look at this, falls, but the rate at which it falls is increasing. Rate is increasing. That means initially it drops slower. Can you see? But when you come to the end of the graph, it's faster. So little by little, the rate is increasing. Basically, the gradient, value of gradient, slope increases. Initially, the slope is more flatter. But little by little, that becomes steeper and steeper. So the rate increases. It falls. The value decreases. The value decreases. But the rate at which it decreases is increasing. That means initially it's falling slowly. And then it falls faster. What about this one? Here also the value is falling. Value is falling. Y value falls, but the rate at which it falls is decreasing. Decreasing means initially it's falling very fast, but little by little the rate at which it falls reduces. Can you see the slope? Slope reduces. Right. This is the graph. This is the sort of graph that I am talking about now. Temperature will fall, but it will not fall at the same rate. Initially it falls faster, then it will fall slower. Why? Compared to the room temperature, excess temperature is high initially. So it falls faster. Little by little, the excess temperature compared to the surroundings reduces. So the falling rate also has to reduce. Right? So come back here. This is the graph we are going to draw from the experiment. You measure the temperature maybe every 10 seconds or every 30 seconds. Every 10 seconds could be too fast. So what we will do, we will measure at every 30 seconds, half a minute. So this is half a minute. This is 1 minute. This is 1.5 minutes, 2 minutes. Right? Mark the points. When you mark all the points, what you will see the graph? A graph in this shape. A graph that falls, but the slope reduces. Initially it falls faster, later it falls slower. A graph in this shape you will get. Still, it doesn't verify Newton's cooling law. What we have to do after this, we are talking about d theta by dt, right? Delta theta by delta t. So at certain points, we have to find the gradient. You know the meaning of gradient. Gradient means you draw a tangent at each point. Let's say at this point, if you want to find the gradient, draw a tangent. Find the gradient of that. M1. Also get the theta 1 at that point, theta 1. At another point, right, at another point, find the theta 2. Now this has a different slope, can you see? Find the gradient of that, M2. Likewise, select 4 or 5 different points like that, find their temperature and the gradient. Why? After finding the gradient and temperature, look at this. Now what you have, the gradient you have, right? Gradient is what? Now these are the calculations you have done already. What? You have taken 5 different temperatures and you have the gradients. At each point you have the gradient. Gradient means what? Gradient is actually delta theta by delta t, because theta versus t graph that was. Theta versus t graph. You take the gradient means that's delta theta by delta t. So basically what we are going to mark in the x-axis is delta theta by delta t. And what we have to take in the y-axis must be theta minus theta r. Theta r we already measured, room temperature. Theta means, when you are measuring the first one, theta 1. Say theta 1 minus theta r, and you have the gradient for that, m1. Take the second one, theta 2 minus theta r, m2. Likewise, mark all 5 points. When you mark all those 5 points, what we expect as a graph is a straight line. The expected graph is a straight line. Once we get the straight line graph here, then we can say, come on, Newton's cooling law is verified. Why? What did Newton say? d theta by dt, cooling rate, is proportionate to theta minus theta r. That means cooling rate versus theta minus theta r graph has to be a straight line. We do the experiment, we get the readings, we draw the graph. So we can't straight away draw this graph. First we have to draw the graph theta versus time. At 5 different points we have to measure the gradient. Then gradient versus theta minus theta r graph has to be drawn. And if we get a straight line, then that verifies, yes, Newton's cooling law is true. Right? It's quite a long process. Like doing the experiment could be simple, but taking the values, analyzing, doing the graphs can be a lengthy process. We have to do it very carefully to finish this experiment. Right? Look at the steps. So I showed you the setup here. You can see either this setup or this setup you are going to do, whichever is convenient for you. Fill up to about 1 centimeter from the top of the calorimeter with water, heated to about 80 degrees centigrade. Think, why do we have to keep it up to 1 centimeter? That means almost up to the top, up to the brim of this calorimeter. Just 1 centimeter below the brim, I am asking you to fill the water. Why is that? Imagine you take the calorimeter and you have filled it only to half or 1/3 of the calorimeter with water. And this water is at 80 degree. Then I can say this part of calorimeter surface will be at 80 degree. But there is no guarantee that this part will be 80 degree, because there is no water in contact with the calorimeter. So what practically would happen there, after this the temperature will not be uniform, it will not be 80. Slowly it will start falling to 70, 60. The calorimeter surface will not have same temperature all through the surface. So how do we ensure the entire calorimeter surface is at 80 degree? Fill water as much as possible. Then why not fully? Why do we have to keep it 1 centimeter below? Otherwise, when you are stirring it, you may not be able to do it comfortably, because the water will start dripping out. That's why keeping some space to keep the thermometer, to keep stirring and all that, we keep 1 centimeter gap for us and fill the rest of it with the hot water. Yes? Fill up to about 1 centimeter from the top of calorimeter with water, heated to about 80 degrees centigrade. Close with the lid and suspend from the stand as shown in the diagram. This or this, whichever. Allow the calorimeter and contents to cool by the continuous flow of air from the electric fan placed near the calorimeter. You can do that. If you don't have the electric fan, the old books used to say keep it near the window, even that is fine. While stirring the water continuously, observe and note down its temperature at 30-second intervals. It has to be equal interval. Okay, 30-second you are not doing, let's say you are doing it at 20-second. So every 20-second you have to measure the temperature. Temperature falls to about 40 degree. Like we usually stop the experiment at around 40 degree when the room temperature is close to 30, because from 80 to 70, 60 it falls faster. 50, 40 it falls at a moderate speed. After 40, the rate at which it falls will be so low. It will take a lot of time to drop 1 degree. So it will take a much longer time. The errors in the experiment can increase. So we don't let it until it comes down to room temperature. We usually stop the experiment at around 40. Measure the room temperature theta R. Draw the temperature versus time. I told you temperature versus time graph. Theta versus T, or capital T versus T. Measure the gradient at different points and draw the gradient versus temperature difference. Gradient versus temperature difference. Gradient is what? The cooling rate. d theta by dt, delta theta by delta t. That's the gradient. And what has to be in the x-axis when you are drawing the graph second time? It has to be the temperature difference, T minus theta R. If it is a straight line graph, then the Newton's law of cooling is verified. So objective or expectation is that we will get a straight line graph, right? So this is all the steps in this experiment are, right? Now let's see how we are going to do this experiment. The apparatus required for this experiment, we need water. Using water only we are going to verify the cooling law. We need a calorimeter. The surface has to be polished so that the radiation doesn't happen. A polished surface with the calorimeter with polished surface. It has to have a lid as well, because the convection has to be prevented. Because the Newton's cooling law we are going to verify for conduction of heat only, right? So radiation, convection should not happen. Radiation is prevented by having polished surface. Convection is prevented by having a lid. Then we need a stirrer, because we have to keep stirring, otherwise you can't confirm uniform temperature within the water. So until from the time we start the experiment until we finish it, the water has to be continuously stirred. Otherwise what will happen? At the surface of the temperature, at the surface of water there will be one temperature. Within the water, in the middle of water, there will be another temperature. To ensure there is uniform temperature throughout the water, you have to keep stirring it. So we need a stirrer. A thermometer to get the temperature measurements. When we draw the graph theta against t, the time has to be measured. Usually what we do, every 30 seconds we get the readings. So to measure time, we need a stopwatch. And then we need a fan. Why do we need a fan here? Newton's cooling law is applicable under two different conditions. Condition number one, you can have constant airflow. If there is constant airflow, then the Newton's cooling law is applicable. If not, if there is no constant airflow, then you have to maintain the environmental conditions unchanged. The environment around this calorimeter has to be unchanged. So you have two options. You can do the experiment with unchanged environmental conditions, or you can do it with constant airflow. Here I have selected to do the experiment with constant airflow, because the precision will be better if we do with constant airflow. But equally you can do with unchanged condition as well. At the end of experiment, I will show you how we do this experiment without the constant airflow with constant environmental conditions. So we are having a fan here to maintain constant airflow. Plus we need a stand because we will be hanging this calorimeter and water on this stand, and we will maintain the airflow, right? So this is all the apparatus we need. What are we going to do first? I told you we are going to start the experiment at 80 degrees. Let's heat the water to 80 degree. From 80 degree until it cools down to 40 degree, we are going to measure the temperature. So what we will do first, we will heat the water to a temperature above 80, let's say to 82, 83 degrees, we will heat it up, and then we will just wait until it comes down to 80. Sharp at 80, we will start the stopwatch and start writing the temperatures. Let's see how we are going to do that. Students, you can see I have got the water heated. It was almost at the boiling temperature. So it will be for sure above 80 degrees. Let me fill the calorimeter with the water. When you are filling it, usually we keep the water level just 1 centimeter below the surface, below the top of this calorimeter, right? From this edge of this calorimeter, from the brim of this calorimeter, 1 centimeter below water surface has to be there. So let's fill it like that first. It's there 1 centimeter below the brim of this calorimeter, water level is there. Let's fix the lid so that the convection doesn't happen. When you are fixing the lid, make sure you already kept a stirrer into that and a thermometer to measure the temperature. Lid with the stirrer. Let's also have a thermometer. Initially, let's check the temperature. I believe it will be above 80 degrees. So we have to wait until it comes to 80 degree. Let's check the temperature now. It is at 84 degrees now. It is at 84 degrees now. We have to wait until it comes down to 80 degree. Let's keep stirring it and wait until it comes to 80 degree. Sharp at 80 degree, let's start the stopwatch. Right? Meanwhile, let's switch on the fan as well. You know why we are switching on the fan? To ensure constant airflow. To ensure constant airflow. The airflow comes towards this calorimeter. From the start of the experiment until the end of the experiment, we have to maintain constant airflow so that the conditions do not change. Right? So now it is at 84. Let's wait until it comes down to 80. From 80, let's start writing down the temperatures every 30 seconds. Students, we have to wait until it comes to 80. It is just above 80 now. Sharp at 80 degrees, let's switch on the stopwatch. And then every 30 seconds, we have to measure the temperature. Let's keep mixing it or stirring it. All right. Now you can see the temperature is now at 80 degrees. Let's start the stopwatch. Let me write the first one, 80 degrees. Keep stirring it. Watch the stopwatch. Sharp at 30 seconds, you have to write the next temperature. Don't forget to stir it continuously. Otherwise, the temperature will not be uniform. It will not be constant throughout the water. Now it is 77 degrees. 77 degrees. Make sure the fan remains switched on so that the continuous airflow, constant airflow is maintained. Now I have to wait for another 30 seconds. That means at 1 minute I can write the next reading. Now it is 74 degrees, 74 degrees. Keep stirring it for next 30 seconds. Now you can see the temperature is dropping by 3 degrees. Each 30 second temperature drop, the cooling rate is 3 degrees. Now it is 71 degrees, 71. We are maintaining constant air flow. That's why the fan is being used. Every 30 seconds at equal time interval, I am measuring the temperature so that I can draw the graph. It is 68 degrees now, 68 degrees. Keep stirring it. We started at 80 and our target is 40 degree. Why do we stop at 40? When it comes closer to the room temperature, the cooling rate will be very low. So you may have to wait for a longer time for the temperature to drop by half a degree or 1 degree. That's why. Now it is 65.5 degrees. 65.5 degrees. Next 30 seconds. Don't stop stirring it, continue stirring it. Now it is 63 degrees, 63 degrees, 63. The fan maintains the constant air flow. The next 30 seconds. Now it is 60.5 degree, 60.5 degrees. Next we have to take at 4 minutes. That means the 8th reading we are taking, 8th reading at 4 minutes. It's 58 degrees, 58 degrees, 58 degrees. You can do this experiment in constant airflow or without the airflow, constant environmental conditions. We are doing it with constant airflow. That's why we are using the fan, you know that. 56. Now you can see here, originally it was falling by 3 degrees. Now it started falling by 2 degrees only. Why? The additional temperature compared to the environment is less now. When it was 80, the additional temperature is high. Let's wait until 5 minutes. That is the 10th reading we are going to take. It's 54 degrees. 54 degrees. Also make sure you don't change the speed of the fan. If you have kept it at a particular speed, until the experiment finishes, you have to maintain the same speed because constant airflow. Right? Don't change the speed of the fan while the experiment is in progress. It's 52 degrees now, 52. I'm getting the temperature readings every 30 seconds, every 30 seconds. Our intention is we are going to draw theta against T graph, temperature versus time, temperature versus time. $50, 50 degrees. We have to keep doing this until it comes down to 40. Since I have the fan, the constant airflow, the cooling rate is higher. If you don't have the fan, the cooling rate would be lower than this. It might take more time for it to become 40. 48.5. 48.5. 48.5. Actually, there is no 0.5 mark on the thermometer. So when it was in between 48 and 49, I assumed it to be 48.5. 47 degrees. 47 degrees. You can see the cooling rate has reduced further. Now only 1.5 centimeter drop each 30 seconds. Initially it was 3 degrees. 45 and a half. 45 and a half. This many points would be actually enough, but then we'll continue until 40 degree. Now 8 minutes are going to be over. 44 and a half. 44.5. Keep stirring it to maintain the uniform temperature within water. 43.5. Now 9 minutes are going to be over. 42.5. 42.5 degrees. Another 2.5 degrees drop, but it might take longer time because the additional temperature compared to the room temperature is much less now. 42 degrees. 42. The fan continues to work at the same speed, doesn't change because we are maintaining constant airflow. Constant airflow. 41.5. Keep stirring it, keep stirring it. 41 degrees, 41. Let's see whether we can wait until it comes to 40. Theoretically, it doesn't necessarily have to be 40. This much of points are enough to draw the graph. Anyway, we'll stop it at 40. 40.5. 40.5. You can see the cooling rate has reduced a lot. It reduces only 0.5 by 0.5 now, because the temperature difference is much less. At the end of it, we will measure the room temperature also, because we need that to find the additional temperature. Yes, it is at 40 degrees now. It is at 40 degrees now. Now we can draw the graph with this many points. You can see we have started at 80 degree. Each of these readings I have written at 30 seconds gap. So in the x-axis, you can take time at 30 seconds gap. You have all these points. Y-axis is going to be temperature. We can draw this graph. But then for the second graph, where you are going to draw delta theta by delta t in the y-axis, that is the cooling rate at the y-axis, and additional temperature in the x-axis. For that, you need the room temperature, because we are going to compare these points with the room temperature to find out the additional temperature. So now let's see what is the room temperature. Students, the room temperature is 28.5 degrees is the room temperature, right? It remains constant without changing at the temperature, 28.5 degrees. Let's write down that temperature, 28.5. Theta R, room temperature, 28.5 degrees centigrade. Right? So now we have got the room temperature, and the water from 80 degree to 40 degree, when it was cooling, we have noted down its temperature every 30 seconds. As I already explained to you, you can draw the graph. First, theta against t, temperature against time graph can be drawn. From that, at least at 5 different points, we can get the delta theta over delta t. Basically, that graph's gradient at 5 different points, at least 5 different points. Then at each of those points, you calculate the additional temperature compared to the room temperature. Now you can draw the graph, the gradient versus additional temperature or temperature difference. Gradient means that is delta theta by delta t. In the x-axis, you take additional temperature, that is the theta minus theta r. Draw the graph. That has to be a straight line according to Newton's cooling law, which is what we are going to verify. Shall we draw the graph and see how it is? You all can see the readings that we have got in the experiment. I have put it in a table here, right? Starting from here, this is the first reading, second, third, fourth, fifth, sixth, seventh, likewise it goes until it comes down to 40 degree. We have written it on the table. Yes, now we are going to draw the graph. Let's see how we can draw the graph. And the y-axis, right, x-axis is time in minutes. Before you draw any graph, marking the axis is the most important thing. Theta in degrees centigrades. With the units, you have to mention what you are drawing. Time, how much time we have taken, you can see 1 from here to here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So that's 11 and a half minutes. Yeah, 23 half-minute slots. So let's see how much cells we have here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 24. Let's bring 12 minutes here. Then this has to be 1, 2, 4, 2, 2, 4, 3. No, right? You need to have 12 minutes there. We'll make it 2, 4, 6, 8. This will be 10 then. 2, 4, 2, 4, 12. See whether that is okay? 1, 3. Likewise, it goes on. And in the y-axis, we need temperature. We don't necessarily have to start from 0 because the lowest temperature we have is 40. Lowest is 40. So we don't necessarily have to start from 0. Highest is 80. 80. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We'll take this point as 80. And here we'll take 40. Starting point we'll take it as 40. Then 40 to 4. Let it be 50 to 4. How many cells we had? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So in 20 cells, we are going to mark 40. So each we can take it as 2. So this will be 44, 46, 1, 2, 3, 4, 5, 50. 1, 2, 3, 4, 5, 60. 1, 2, 3, 4, 5, 70. 1, 2, 3, 4, 5, 80. Shall we mark all the points? The first point was 80. At time 0, it was 80. The second point, 77. In half a minute, it was 77. 70, 72, 74, 76, 77. 74, 71. 76, 74. 71, 71. 68, 65.5. 68, 65.5. 62, 64, 65.5. 65.5. 63, 60.5. 63, 62, 63, 60.5. Yeah. 58, 56, 54. 58, 56, 54. 52, 50, 48.5. 52, 50, 48.5. This is 48, 48.5. 47, 45.5. 47, 46, 47. 45.5. 44.5, 43.5. 44.5. 43.5. Then you have 42.5, 42. 42.5, 42.5. 42. 41.5, 41. 41.5. 41. 40.5, 40. Carefully you have to mark all these points, 40.5 and 40. That's how the points are. As we expected, it's coming in a shape of curve. where the slope drops. Let's draw the graph now. Let's draw the graph. Right, that's the graph we are getting with all the points. As expected, it's a curve. It's a curve. It's not a straight line, and the slope also drops. Slope also drops. Now what we have to do, at 4 or 5 different points, I need to find the gradient. This is just the theta versus time graph, right? We have to draw now the gradient versus excess temperature. So to find the gradient, let me take another color. Maybe I'll connect these 2 points. Yes. So basically these two. Right. Then another one. These 2 points. Or even these 2 points will be better. Yeah, these two. Okay, that's another point. We need to take 3 or 4 points at least. 4 points at least. So we'll take another 2 points here. Yeah. And another one here. I'll tell you after doing the graph completely, I'll show you there is a special method of drawing the gradients when you are drawing it in a book. Like how you find the gradient, how you find the tangent for a curve using a piece of mirror, right? I'll show you, but for now we will use this method. Right. For each of them, I need to find the temperature. So see, when I am considering these 2 points, let me take the midpoint as the temperature. Yes. Is it the midpoint? Yes. And when you are considering these 2 points, the midpoint again. And now you are considering these 2 points, so the midpoint, right? Midpoint. The midpoint. Let's do the calculations. I need to find the theta values. The first one, I'll take this as the first one. This is at 44. 44. Second one, this is 52. 54, so it has to be 53. Third one, see, this was 58. Before 58, what was the reading? 60.5. So 59.25. Approximately 59 it is it? 59. And this one, this is 68. 68. And before 68, 71. So the midpoint would have been 69.5. Those are the 4 temperature points I am taking. Each of those points I need the gradient. Gradient here, the y difference. Look at the y difference. This reading, this was at 43.5 and this was 44.5. So in between these 2 points, look at the points again. These 2 points, the drop was 1 degree. I am taking d theta by dt. Drop was 1 degree. In how much time? Each cell is half a second, right? Half. So that is 2. Check the points again. We have 43.5. Check this. 43.5, 44.5. Yes. And I'm talking about these 2 points where the temperature drop is 2. Temperature drop is 2. In how much time? See, look at these 2 points. 2 is the temperature drop in 1 cell. 1 cell means half a minute. So that is gradient of 4. Now here, we'll take these 2 points. This was 58 and before 58 we had 60.5, is it? 58, 60.5. So 2.5 is the temperature difference there. And that is also in half a minute difference. Half. 5 is the gradient. 69.5 here. Look at these 2 points. This is 68, 71, 3 in half a minute. Gradient of 6. Gradient of 6. This is theta. So let me write theta minus theta r also. Let me write it here, theta minus theta r. 44. The room temperature, theta r was 28.5. So 44 minus 28.5 is 16, 15.5. 15.5. Right? 53, 28.5 will be 24.5. 59, 28.5 will be 30.5. 69.5, 28.5 will be 41.5. 41. Now this is going to be in the x-axis, this is going to be in the y-axis. Right? Let's take the x-axis and the y-axis. This is theta minus theta r. This is the delta theta by delta t. Its maximum we have up to 41. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We'll take up to 50 then. So every 2 has to be 5. 10, 15, 20, 25, 30, 35, 40, 45, 50. And delta theta by delta t we have up to 6. 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We will mark 1 here, 2, 3, 4, 5, 6. First one, at 15.5 it is 2. 15.5 it is 2. 15.5 it is 2. Like that. Right? Second one, 24.5 it's 4. 24.5 it's 4. 24.5 it's 4. Right. Third one, 30.5 it's 5. 30.5 it's 5. 30.5. 30.5 it's 5. Next one. 41 it's 6. 41 it's 6. 6 at 41. 40, 41. That's all the points we are getting. Right? More or less it is a straight line going through the origin. There will be small deviations, as I always say, and when we do the experiments you can't get exactly all the lines falling on all the points falling on the line as we study in the theory. There will be little bit of deviations. Let me see the best line that I can draw with these points. Yeah, a line like that would be the most suitable line. Deviations are not very significant, like small amount of deviation that can be assumed to be practical error. Imagine if you have got 4 points like this, one here, one here, one here, one here, then there is no straight line, no regression as anything, right? Here we can see there is a pattern, you can see it's more or less very close to a straight line. It's not exactly on the straight line, little bit of deviation, that's very much acceptable when we do experiments under practical conditions. Right? So now since we have got the graph d theta versus dt, d theta by dt versus theta minus theta r, it is a straight line going through origin. Therefore, Newton's cooling law which states that cooling rate, which is d theta by dt, is proportionate to theta minus theta r, is verified. Now, before we go to the past paper questions, I want to show you something else. See here, we found the gradient at each point, right? To find that gradient, there is another method. Sometimes they can ask you in an exam question. You are given this graph, theta versus t graph, and a piece of mirror is given. How would you use the mirror to find the gradient of it? Right? So, let's see how to find that. Method to find the gradient. Place the mirror on the curve at the point where we want the tangent such that its reflecting surface is perpendicular to the plane of the paper and is facing you. Now look at this. Let's say this is the graph you have drawn. Say this is the graph, right? Now at this point you want to find the gradient. Now we drew the gradient approximately, right? So what they say, you keep the mirror like this. Keep it like this, right? And if you are keeping your eye from this side and observing it, keep the reflection side to your side. You must be able to see through the mirror. Then, now look at the curve just in front of the mirror and its reflection, and think of this curve and its reflection as one continuous line. What that means is, see now when you are looking from here, you are not going to see this part of the graph. You can't see what is behind the mirror. What you will see, this graph and the reflection of this part of the graph on this mirror, right? So what will happen? Okay, let me draw this mirror in an angle, in a different angle, and show you what happens. Let's say you have kept the mirror like this. Now you are observing it from here. Now you are not going to see what is behind you, right? So let me draw that in dotted lines, because this you are not going to see now. Okay, this is behind the mirror. You can't see behind the mirror. Right. Now what you are going to see, this part of the graph and the image of this on the mirror. The image is going to be see, the image will be like this. For each point, the object distance and the image distance have to be equal. From the mirror, this point's image will be here. This point's image will be here. So, you will see the reflection. Now, look at this. If you consider this as the same graph, can you see there is a kind of a kink. Kink means there is a break there, like graph comes, it breaks, there is a corner and it goes in another direction. It doesn't go like a continuous graph, right? It doesn't go like a continuous graph. That's what they say. You would see that this continuous line has a sharp point at the point where the curve meets the image of the mirror, in the mirror. So this is the image, this is the curve. When they both meet, there is a curve. Now what you are going to do, adjust the angle of this mirror. When you adjust the angle of this mirror, at some point you will see something like this. Look at this. Say the graph is this, right? I'll draw the graph in the front part only, right? Now you have kept the mirror. Let's say you have kept it like this, the other color. Say you have kept it like this. Now let's say the image of this is seen like this. Now can you see in this graph, the image and the original graph, there was a sharp edge. There was a like corner, right? In graphs they call it kinked graph, K-I-N-K. That means there is a like break. You don't see that break here. Can you see the original graph and its image? It looks like a continuous line. It looks like a continuous line. At this point, there is no sharp point. What that means is, when you see the graph like this, the graph, this is the image and this is the graph. when you see both of them without a sharp point, if it looks like single continuous line, if it looks like that, that means you have kept the mirror perpendicular to the graph at this point. Right? It's a perpendicular. So what you can do, you hold the mirror and draw the line and say that line is perpendicular at that point. At that point, point to point, the perpendicular is going to be different. Then what you do, now see, you have the graph and you have drawn the perpendicular. Now, again, keep the mirror here, adjust the mirror. So imagine if you kept the mirror like this, and if you observe from here, you will see this part of the graph and its image will be like this. So graph and the image, there is a sharp point. So keep adjusting this mirror, keep adjusting the mirror. At some point, look at this again. This is your graph. You have already drawn the perpendicular using the mirror. Now you are keeping the mirror perpendicular to the perpendicular that you have drawn. Perpendicular to the perpendicular you have drawn already, right? If you kept like this, then you will see this line will look like a continuous line within the mirror, which means now the mirror is perpendicular to the perpendicular that you have drawn. Now draw this line, that will be the tangent at this point. That will be the tangent, right? So this is the idea. They say using the mirror how to find tangent. Let me finish reading it. So what it says, now move the mirror such that this sharp point is eliminated. The curve moves onto its image smoothly. This happens when the curve is perpendicular to the mirror at the point where it meets the mirror. That's this case. Since the curve is perpendicular to the mirror, its image is also perpendicular. That's why you see it as a continuous line. Consequently, there is no sharp point at the point where the curve meets at its image. Now, draw a line along the length of the mirror intersecting the curve. This line is normal to the curve. Normal to the curve at the point of intersection. Now, rotate the mirror by around 90 degrees such that base of the mirror passes through the point of intersection of the curve and its normal. Look at the normal in front. Look at the normal line. The perpendicular line you have drawn, normal line. Look at the normal line through the mirror, in front of the mirror and its reflection. Adjust the mirror such that the normal in front of the mirror and its image forms a straight line. At this position, the mirror is perpendicular to the normal. Draw a line along the length of the mirror intersecting the normal. This line is tangential to the curve at the point of intersection. Right? So that's how. Suppose if they ask you how will you use a mirror to draw the tangent of a graph at a point, this is what we do. Keep the mirror and the graph you see and its image must look like the same line. If you can see that without a sharp point there, without a break there, if it looks like a continuous line, then the mirror is normal to the graph. Draw the normal. Then turn it approximately by 90 degrees. Look at the mirror such that the normal line you have drawn and its image go as a continuous line. Once you have adjusted the mirror like that, then the mirror is perpendicular to the normal. That means it is tangential to the graph at that point. Clear? So just have that idea as well. In case if it is tested in an exam, you must be able to write it. Okay? Right. So that's all in that experiment. Now we will see a past paper question that has come from this section. There is one past paper from 2017 exam. Let's see what question was it. The diagram shows an experimental setup that can be used to verify Newton's law of cooling and to determine the specific heat capacity of a given liquid. It consists of a calorimeter with a lid and a stirrer made of copper, heated water thermometer and a stand to hang the calorimeter setup. An experimental procedure similar to the method used in the standard experiment is performed by keeping the setup closer to an open window of the laboratory. The advantage of doing this experiment near an open window where you get a slow, uniform flow of wind, see, constant flow, uniform flow of wind, is that you can verify the validity of Newton's law of cooling for higher temperature differences. Because otherwise, when the temperature of the content is very high, it will lose heat at a very fast rate. Then what happens? The surrounding might change a little bit. If the environmental room temperature is 30, if let's say some substance, forget about this water, some substance, let's say you have heated to 200 degree. So from 200 degree when it releases, the excess temperature is 170, right? Huge excess temperature. So it releases heat very fast. So when the room temperature is 30, sometimes the near surrounding of that object might be above 30 for a moment, because it gets heat at a fast rate. So how do we avoid that happening? That means the surrounding getting heated. How do we avoid that? Have continuous flow of air. So whatever the heat that comes in, comes to the surrounding, will be taken away with the flow of air. Right? That's why they say it's very useful. It's particularly useful when verifying this law for a high temperature. What are the readings you would take in this experiment to verify Newton's law of cooling? Simple. Room temperature you have to take and the temperature of this water at constant intervals. Room temperature and temperature of water at constant intervals. You don't necessarily have to say every 30 seconds, but constant intervals. Next. What is the experimental procedure to be performed which enables you to reliably assume that the reading of the thermometer is same as the temperature of the outer surface of the calorimeter? I explained this in the theory when I was doing the experiment also. I was explaining why are we stirring it, to ensure the water has uniform temperature as well as the outer surface of calorimeter and water have the same temperature. Because heat loss, we are mainly talking about the outer surface temperature, but we can't measure that. What we measure is the water's temperature. So how do we ensure water's temperature and the outer surface temperature are same? By stirring it. How do you ensure that? By stirring continuously. Next, draw rough sketches of two graphs that you would plot to verify the Newton's law of cooling. Label the axes properly with the appropriate units. See, this is what I told you, right? What is more important is to understand the experimental procedures. How do we do the experiment? What graphs are we getting? So don't be too concerned about are we exactly getting the theoretical value? Are we getting the graph as exactly what we studied in the theory? No. More than all that, more than the outcome from the experiment, outcome also is important, but more than the outcome of the experiment, how we do the experiment, the step-by-step procedures of the experiment is more important. Understood? So, like anybody followed the experiment when I was doing, would comfortably answer this because I have done all these graphs. What is the first one? Theta versus time will be a graph like this. See a curve, and then theta minus theta r, not theta minus theta r, that has to be in the x-axis, isn't it? Theta minus theta r in the x-axis, delta theta by delta t, and we expect a straight line. Let's define this. Theta r, room temperature, theta, temperature of water, T, time. Commonly used measures, but still better to define it. In order to determine the specific heat capacity of a given liquid, the same procedure used in A above is repeated for the liquid after obtaining relevant readings for water. In the next experiment, when I'm doing it, I'm going to show this to you. It's actually a continuation of this. After verifying Newton's cooling law, what we can do, we can use the same procedure to another liquid of which specific heat capacity is unknown, right? And we can draw the cooling curve for that also. That's what they are telling. What is the reason for using same calorimeter used in part A to perform this experiment? So, like anybody finding it a bit confusing or a bit difficult at this point, make sure you go through my next experiment, right? Using the cooling method, finding the specific heat capacity of a liquid, and then come back and answer this. Part B would be easy for you. So, why do we use the same calorimeter to maintain same area for cooling? Right, the area matters, right? Area matters. Ka theta minus theta r, area matters, yes. Next. Because if you are using different size calorimeter for water and this liquid, then the area will be different. Then you can't assume delta theta by delta t to be same. Understand? Now this is the procedure. Like in short, if I say, now you will be drawing the cooling curve for water, and then you will draw the cooling curve for the other liquid also. At some temperature, right? Let's say a particular temperature, you will find the delta theta by delta t for both of them at a particular temperature. So you find the cooling rate here, m water, c water, delta t by delta t, plus calorimeter is also there, right? This is the heat loss rate. The heat loss rate here will be again calorimeter is there, plus some other liquid is there, right? Cl, let's say, delta theta by delta t. And what we studied in theory, the heat loss rate doesn't depend on what substance is there within that. It depends on the surface area and the type of material and the temperature difference. Ka theta minus theta r is the equation for heat loss rate. Q heat loss rate is Ka theta minus theta r. In the next experiment, I will be discussing this in much more detail. So, if you maintain the same calorimeter, the substance type is same. So, K will be same for both. Same calorimeter, area will be same for both. You are finding the delta theta by delta t at the same particular temperature. If it is 70, 70 here. So, excess temperature is also same, which means both the calorimeter with water, hot water, calorimeter with some other liquid at the same temperature must be losing heat at the same rate. Losing heat, that means Q should be same. dQ by dt must be same. dQ by dt means mc delta theta by delta t. Q means mc theta. So, dQ by dt means mc delta theta by delta t, right? So, equate these two. On this side, you will be knowing all this. Delta theta by delta t you take from the graph. M you can measure from the using a chemical balance or 3-beam balance, you can measure the mass. Cw we know. Cc we know. That is the copper's specific heat capacity. We usually take it as 420 joules per kilogram per Kelvin. Only Cl will be the unknown. We can find it. Right. In addition to the using of same calorimeter, what is the reason for using same volume of water and liquid in this experiment? To ensure same cooling conditions. Both the water and the particular liquid have to be cooling with the same conditions, right? If you use different amount of water, area will be different, cooling conditions will be different. So, same answer again, to maintain same area, same cooling area and cooling conditions. Previous one also we can see same area and cooling conditions. What another cooling condition that we can particularly mention here? Type of material. Because let's say a copper calorimeter and an aluminium calorimeter, even though they are of same size, same temperature, the cooling rate or the rate at which they are losing heat will not be same, because the type of material is different. That's why they say you have to use the same calorimeter. Same calorimeter. Same calorimeter. Next. The mass and specific heat capacity of the calorimeter with the lid and the stirrer are M and S respectively. Mass and the specific heat capacity of the liquid are M1 and S1 respectively. The average rate of loss of heat and the average rate of drop of temperature of the calorimeter with the liquid for a given temperature are HM and theta M respectively. In terms of these quantities, write down the relationship between HM and theta M. So HM has to be HM. What is HM again? Average rate of drop of temperature is theta M. Average rate of loss of heat, HM, must be equal to MS, that's for the calorimeter. And for the water or for the liquid, it is M1 S1 into delta theta by delta T, which is what is theta M. Write down the relationship between HM and theta M. Next. Let M equals 0.15 kilogram, S is 400, ML is 0.25 for a certain temperature difference. The average rate of heat loss of the calorimeter with water was found to be 90. Average rate of drop of temperature of the calorimeter with the liquid for the same temperature difference was found to be 0.125 kelvins per second. Determine the specific heat capacity. Let me write the same formula again. MS plus M1 S1 or ML SL, whichever, into theta M. HM is given to be 90 joules per second. M 0.15, S is 400, ML 0.25, SL or S1 is what they are asking you to find. Theta M is 0.125. Solving this and finding S1 or SL. When you divide by 0.125, dividing by 0.125 and multiplying by 8 are same, because if you multiply this by 8, it's 1. 0.125 into 8 is 1. Multiply other side also by 8, 720. Now this is 60 plus 0.25 S1. Now 0.25 S1 will be 60 subtracted will be 660 from this S1. Dividing by 0.25 and multiplying by 4 will be same, because 0.25 into 4 is 1. So multiply this by 4 and 4, 660 into 4, 0426. Give the units correctly. Joule per kilogram per Kelvin. You can't put the stroke and minus 1. Now if you put the stroke, the slash, then don't put power minus 1. 2640 joules per kilogram per Kelvin is the answer we are getting for this. 2640 joules per kilogram per Kelvin. Understood? Right. So that's a very simple question. Usually, if Newton's cooling law comes, with that they ask the other part as well. Using the cooling law, how to find the specific heat capacity of another liquid. So better with this, the next experiment we are going to do it together. If you study them together, it will be easy for you to answer the exam questions. So practice this very well, understand this very well, and we will meet up with another experiment soon.